What is the inorganic benzene? Inorganic benzene, which is nothing but a reactions of diborane with the ammonia, which gives rise to a complex compound, which is upon further heating, which gives rise to the inorganic benzene. If it is exposed continuously with the air, it reacts with the atmospheric air, thereby it forms a protective shield around the metal. So boron trifluoride, which has been treated with lithium aluminum hydride in presence of dimethyl ether, it forms what? Diborane. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called some P block elements. Under this unit, we have discussed about the introductory part of this unit. That is, we have understood that where exactly the P block which has been situated, what is the general trends in their periodic property. In addition to that, we have also learned about the general oxidation state, and we also studied about in detail study of group 13 elements and their electronic configuration and some of the periodic properties also we have learned with the boron family. Today we will continue with the some of the chemical properties, and also we are going to discuss with the anomalous behavior of the boron. After understanding the anomalous behavior of the boron, we are going to understand some of the important compounds of the boron. So, okay, they are nothing but a borax, orthoboric acid and diborane. In all these three compounds, we are going to discuss with their preparations and some of the important properties. And also, we are going to discuss with the structure of diborane and uses of the boron and its compound. We are going to discuss in this session. Okay. So first we will see the chemical property. In that we are going to understand the oxidation state. So already we have understood that if you see the group 13 elements, all these elements, this shows the outermost electronic configuration of Ns2Np1, which indicates that in its outermost shell, it consists of 3 electrons. Hence it shows the +3 oxidation state. Correct, no? The atoms of all this element, they have a 3 valence electron, as I have explained. 2 electrons are present in the s orbital and 1 electron which is present at the p orbital. Hence it is known as a p block element. Correct? No? Therefore, all this element can show the maximum oxidation state of +3. The common oxidation state observed for the group 13 elements are +3 and +4. Except barium and aluminum. Why it is showing a +3 in addition to +1? That is mainly because of the stability of +1 oxidation state increases in a sequence of aluminium, gallium, indium as well as with the thallium. So, if you see that the general outermost electronic configuration is Ns2Np1. Okay. But as we move down the group, that is from the first element, a boron, next is aluminium, then gallium, indium as well as with the thallium. Okay, as we move down the group, the stability of this +1 oxidation state will be increases. Why this +1 oxidation state stability increases? Because as we move down the group, what will happen? The atomic number which is also get increased. Since the last electrons are going to add up with the Np, that is to the p orbital, the stability of the +1 oxidation state will be increases. And meanwhile, what will happen? The stability of +2 oxidation state will be decreases. Why it is decreases? As we move down the group, again atomic number which is increases. As the atomic numbers are increases, the number of electrons are added to the p orbitals only. So that p orbital stability will be increases with the +1 oxidation state. But as we move down the group, the Ns2 electron, the 2 electrons which is there in the s orbitals, it is completely become inert. Due to the inertness means it do not react with any other element, thereby it do not share its electron, or it accepts the electron, or it will donate the electron. Due to this inert pair effects, the stability of +2 oxidation state will be decreases down the group, and stability of +1 oxidation state will be increases down the group. Okay, and this stability order will be like this. Except boron, you can see that aluminium, gallium, indium and thallium will have a maximum +1 oxidation state. Okay, this is mainly because of the inert pair effect as I have explained. Next is reactivity towards the halogen. Let's see how this group 13 elements which also reacted towards the halogen. All the group 13 elements form a trihalides. What does it form? When it is react with the halogen, it forms a trihalide of a general configuration of MX3 by combining with the halogen atom except thallium. Except thallium, all the elements like boron, aluminium, gallium, indium and thallium. Except this, all these elements can also react with the halogen, thereby it forms what? Trihalide. It forms a trihalide. You can see that M stands for the elements. Okay, it may be boron, gallium or anything of the group 13. So you can take the example of aluminium. Okay, I'll go with the aluminium. So aluminium can react with the chloride, that is an halogen. It forms AlCl3. Correct, no? So AlCl3. So this is how we will balance it. Okay, so this is how when the group 13 elements, when it is react with an halogen, it forms a trihalide. You can take one more example by taking the boron itself. You can go with the fluorine. Okay, so it formed BF3. Okay, so boron trifluoride will be formed. Boron trifluoride. Okay, this indicates that when it is react with an halogen, it forms a trihalide. Okay, the product will be trihalide in nature. Due to the smaller size and a high electronegativity of boron, all the boron halides are covalent and they behave as a Lewis acid. So, because of the covalent nature, they behave as a Lewis acid, and because of the smaller size also and increasing in electronegativity characters, they behave like a Lewis acids and they exist as a monomeric molecules having the planar triangular geometry with the sp2 hybridized nature of the boron. All the boron trifluorides, except BF, they are hydrolyzed to give a boric acids. You can see that this is a boron trifluoride. You can go with the boron F3 also, boron trifluoride also. Except boron trifluoride, you can go with the boron trichloride also. When it is hydrolyzed within water, it gives rise to what? Boric acid, that is BOH thrice with 3 HCl. Okay. So, this indicates that except boron trifluoride, boron halides can hydrolyze within water to give a boric acid. What is the name of this compound? Which is a boric acid. Next, we have the structure of the boron. Okay. The boron atom in a boron trifluoride I am talking. So, boron trifluoride will be generally represented as BX3, where X will be chlorine, bromine or iodine. Okay, except fluorine has 6 electrons in its outermost orbital, thus it can accept the pair of electron. So, in a BCl3 or in a BR3, in all these elements, the boron will consist of 6 electrons in its outermost shell. In order to get an octet structure, it need to accept the 1 electron pair. Correct, no? Pair of electron from the donor molecules like ammonia to complete the octet structure. Hence, the boron halides act as a very efficient Lewis acid. So, why does they act as a Lewis acid? It need to accept the 2 more electron to get the octet structure. The relative Lewis acid characters of the boron trihalides will be obeys in this order. It will be in the order of boron iodide, that is boron triiodide, boron tribromide, boron trichloride and boron trifluoride. Except this, you can see this order, highest it is there for the boron iodide, that is boron triiodide. Okay. The halides of the group 13 elements have a halogen-rich dimeric structure as I have represented with this by taking the aluminium dimeric structure, that is aluminium 3 chloride. You can see that this is a AlCl3 structure where you can see that The aluminium is a group 13 elements. So, in order to get the stable electronic configuration of the octet structure, it need to accept the one pair of electron from the donor atoms. Thereby, it forms its planar structure. Correct, no? So, here, if you see that aluminium trichloride, okay, or you can say that aluminium trichloride, which exhibits in a dimeric form, that is, it exhibits in Al2Cl6. You can count here, there are 2 aluminium atom will be there and 6 chlorine atom will be there. So, it exhibits in a dimeric structure. Each aluminium atom, you can see that this is a 1 AlCl3, you can see that this is a 1 AlCl3 and you can see that there is a 1 more AlCl3, correct no? So, this aluminium atom can accept the 1 electron from the neighboring chlorine atom. Similarly, this aluminium atom can accept 1 pair of electron from the neighboring chlorine atom. Thereby, it exhibits in a dimeric structure, hence it is written as Al2Cl6. Why it is exhibits in a dimeric form? Because in order to get a stable octet structure, you know, the group 13 elements and their halides, they are exhibits in a dimeric form. Next, we have reactivity towards the air. The boron, if it is in a crystalline form, you know, it does not react with an air. But the amorphous form can also react with the air. Thereby, it forms a B2O3. B2O3 is nothing but a BORAX. Okay. So, amorphous boron upon heating with an air, it forms a B2O3. So, you can see that boron, it is in a amorphous form. When it is react with the atmospheric oxygen, it forms a B2O3. So, aluminium can also react with an air to form a oxide layer. You can see that when it is react with an oxygen, it forms a boric oxide. Correct, no? Oxide layer on the surface which protects the metal from the further attacks. This is also known as passivity. If you take the aluminium, imagine this is an aluminium metal. If it is exposed continuously with the air, it reacts with the atmospheric air. Thereby, it forms a protective shield around the metal. Okay, and thereby, you know, it do not allow the remaining part of this metal to react with the air. This process we call it as what? Passivity, which we can observe only in case of the aluminium. The aluminium forms Al2O3 upon heating with an water. You can see that 2Al can react with an oxygen molecule, thereby it forms a Al2O3. This indicates that even though we are taking an aluminium, if it is react with the atmospheric oxygen, it forms a aluminium oxide. Next, we have reactivity towards the acids and alkali. Okay, boron does not react with an acids and alkali even at a moderate temperature, but aluminium dissolves in a mineral acids and aqueous alkali and shows a amphoteric nature. So, in your 10th standard also hope you studied that aluminium oxide, which is amphoteric in nature because it can easily react with an acid or thereby it can easily react with a base to form a salts and water. Correct, no? So, let's see with the reactions of aluminium with an acids. Okay, aluminium dissolves with a dilute HCl to liberate the hydrogen gas. You can see that aluminium, when it is react with an aqueous solution of acids, you know, it forms a liberations of hydrogen with the aluminium will be get reduced to AlCl3 and it donates 6 electrons to the chlorine. Okay, but concentrated nitric acid renders the aluminium passivity by forming a protective layer on its surface. Okay, next we have the reactions of aluminium with the base, that is with the alkali. Aluminium can also react with the aqueous alkali to form a sodium tetrahydroxyaluminium 3 by liberations of hydrogen gas. You can dihydrogen gas. You can see that aluminium can also react with a base in presence of an water molecule. It forms what? Sodium tetrahydroxyaluminate. If you see this compound, this is a complex compound. So, more about this coordination compounds you are going to understand in your second PUC. In addition to that, you can see that there is a liberations of hydrogen. So, by understanding these two reactions, we can clearly understand that aluminium, which is behave like a amphoteric acids, are amphoteric in nature because it can it can react with an acid, it can also react with a base, thereby forms a respective compounds. Next is anomalous behavior of the boron. While discussing with the general properties of the group 13, I have informed that all the elements except boron, they are metal in nature. Boron is only the non-metal which is there in this block. Correct? No? Why boron is different from the other element even though it is a non-metal? We'll see what is the anomalous behavior of the boron. Okay, the boron of the first member of the group 13 shows the anomalous behavior. This is mainly due to the extremely low size, and there is a high charge to mass ratio, or you can say that it is a high nuclear charge size ratio and high electronegativity and non-availability of the d orbitals. So this is only the 4 reasons which makes a boron to behave different from the rest of the other elements of this block. Okay, one is availability, non-availability of the d orbital, and also high electronegativity, high charge to size ratio, and because of the small size. Okay, in the examination they can ask you for the 2 marks to write the anomalous behavior of the boron. So boron. Next we have the important compounds of the boron. The first one is borax. The formula of the compounds is Na2B4O7 10 water molecule, and orthoboric acid, that is H3BO3, and next is diborane, that is B2H6. Okay, we'll discuss one by one. First, I'll go with the borax. What is the formula to write the borax? It is Na2B4O7 with a 10 water molecule, and remember it is a white crystalline solid. We'll see with some of the properties of the borax, okay, which is the compounds of the boron. Okay, the aqueous solution is an alkaline due to hydrolysis. If you take the borax, if you do the hydrolysis with an water, it behaves like a strong alkali, and also it forms a H3BO3. Okay. Upon heating, the borax loses its water molecule of crystallization and swells up to form a fluffy mass. Upon further heating, it melts to give a clear liquid which solidified to give a transparent glassy bed consists of sodium metaborate and boric anhydrate, which is known as borax bed. You can see that this is a borax, okay, which is upon heating, it loses its water molecule, thereby it forms Na2B4O7. If you heat this further, so it forms, the name of this compound is sodium metaborate, okay, and this is boric anhydrate, okay, boric anhydrate. The mixture of sodium metaborate with the boric anhydrate, which is known as what? Borax bed. So for your 1 mark, they can ask you, what is borax bed? For your competitive exams also, they can ask you, what is a borax bed? It is a mixture of sodium metaborate with the boric anhydrate. Okay. Next, we have orthoboric acids. The orthoboric acids, the formula is H3BO3. It is a white crystalline solid with a short, a soapy touch. When we touch these boric acids, orthoboric acid, which gives a soapy touch, and it is sparingly soluble in water but highly soluble in hot water. Okay. The boric acid can be prepared by reacting with the borax with mineral acids such as hydrochloric acids. So we are preparing what? Orthoboric acid, correct? No? Orthoboric acid we are preparing, and that can be prepared by considering what? Borax. So this is a borax which has been treated with a concentrated HCl. What will happen? So it will form a boric hydroxide with a formation of, it is also known as what? Orthoboric acids. Orthoboric acids, okay, with the formation of sodium chloride with a release of water molecule. This is the first way to prepare the orthoboric acid from the borax. Next, we have the properties of this orthoboric acid. The boric acid is a Lewis acid which interact with the water molecule to form a tetrahydroxyborate ion. What is the Lewis acid? Which can able to accept one pair of electron. So here our boric acid, when it is react within water, it forms what? Tetrahydroxyborate ion. You can see the tetrahydroxyborate ions. Okay, will be formed. This indicates that boric acid, orthoboric acid, which is a Lewis acid. Upon action of the heat, when it is heated around 170 degrees Celsius, it hydrated and forming a metaboric acids. You can see that this is a H3BO3, that is orthoboric acid. Upon heating, it forms a HBO3 with the formation of water molecule. This is nothing but a metaboric acids. The metaboric acids, which is upon further heating at 276 degrees Celsius, it is heated up to 300 further, and dehydrations will be taking place and leading to the formation of tetraboric acids. You can see that which is upon further heating, it forms a tetraboric acid, which is also known as what? Pyroboric acid. This upon further heating, it gives rise to the B2O3, that is nothing but a boron trioxide. You can rewrite that entire reaction in a single step also. So I'll show you here. H3BO3 upon heating, which gives rise to the HBO2, which is upon further heating, which gives rise to the tetraboric acid, that is H2B4O7, which is further heating, which gives rise to the boron trioxide. So this is a boron trioxide which is formed. So this indicates that which can easily undergo heating and to give a boron trioxide. Okay. Next, we have this crystalline structure of the boric acid. You can see that the orthoboric acid formula is H3BO3. Correct? No? H3BO3. You can see that there are 3 hydrogen atom will be there and 3 oxygen atom will be there, and we have only one boron atom. So you can see that there are 3 hydrogen atom, 3 oxygen atom and 1 boron, and the shape will be extended. So this indicates that between the boron and the central metal atom is a boron. On both the sides, you can see that there is a hydrogen bonding which has been formed with the water molecule. So this is a crystalline structure of the boric acids. Next, we have DIBORANE, which is the last component of the boron. Okay, and it is represented as B2H6. Let's see the method of preparation. DIBORANE is prepared by treating the boron trifluoride with lithium aluminium hydrate in a dry methyl ether. So boron trifluoride, which has been treated with lithium aluminium hydrate in presence of dimethyl ether, it forms what? DIBORANE, that is B2H6, with the formation of lithium aluminium fluoride. Industrially, we can prepare the industrial synthesis which involves the reduction of boron trifluoride by sodium hydrate. So boron trifluoride, which has been undergo reduction with sodium hydrate, it forms what? DIBORANE with the formation of sodium fluoride. In laboratory, a convenient laboratory method for the preparations of DIBORANE involves oxidation of sodium borohydrate with an iodine. Sodium bromohydrate, if you do the oxidation with an iodine, it forms what? DIBORANE with the formation of sodium iodide with the liberation of hydrogen gas. So these are the 3 methods for the preparations of DIBORANE, which are the compounds of boron. Okay. Next, we have physical properties of DIBORANE. DIBORANE is a colorless gas at room temperature with a repulsive sweet odor, and it has a high toxic with a boiling point of 180 Kelvin. DIBORANE can easily catches the fire spontaneously upon exposure to air, and DIBORANE will ignite spontaneously in the moist air at room temperature. Thereby, we can clearly understand that when we expose the DIBORANE with an air, it can easily catches the fire. Thereby, it can spontaneously burn with air. Next, we have reactions with the air. How does diborane can also react with the air? It burns with an oxygen to liberate the hydrogen gas. During this process, the huge amount of heat will be released. Okay, diborane, when it does react with the atmospheric oxygen, it forms a B2O3 with the release of water molecule. You can see that this is a enthalpy change in enthalpy. You can see that it is a very huge. So during that process, huge amount of heat will be released, and it is around minus 1,976 kilojoules per mole. And when it is react with water, boranes are readily hydrolyzed with water to give a boric acids. So diborane, when it is hydrolyzed with water, or when it is treated with water, it forms a boric acid with the liberation of hydrogen. Next, we have reactions with the ammonia. So for the examination point of view, it is very, very important, and it can be asked for 2 to 3 marks. Okay. The direct reactions of ammonia with the diborane, which formulated as NH3 2 times, BH2 plus and BH4 minus. Further, upon heating with the borazine, which is also called as inorganic benzene due to its ring structure. So you can see that when you take the diborane, if it is treated with an ammonia, it forms NH3 2 times with BH3. Okay, with B4H minus ion. This is upon further heating which gives rise to the B3N3H6, which is also known as what? It is known as inorganic benzene. So for your examination, they'll ask you what is the inorganic benzene. Inorganic benzene, which is nothing but a reactions of diborane with the ammonia, which gives rise to a complex compound, which is upon further heating, which gives rise to the inorganic benzene. The diborane undergo cleavage reactions with the Lewis base to give a boron adducts, that is nothing but BH3L. So you can see that diborane, which undergo cleavage reaction with the Lewis base, it forms an intermediate compound. It can also react with the carbon monoxide and forms a BH3CO. Next is structure of the diborane. If you see the structure of the diborane, the 4 terminal of that is diborane is B2H6, correct now? B2H6. The 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane, above and below its plane, and there are 2 hanging hydrogen atoms. To each boron atom forms a 4 bonds, even though it has only 3 electrons. The terminal boron and hydrogen bonds are regular bonds, but the bridge boron and hydrogen bonds are difficult. Each bridge hydrogen is bonded to the 2 boron atoms and by sharing its 2 electrons, and such covalent bonds are also called as 3-centered electron pair bond or multiple bond pair, or it is also known as banana bond. You can see that in a diborane, we can see that there are 2 boron atom will be there. 2 boron atoms are get bridged between the 2 hydrogen atom, and you can see that there are 2 hydrogen atom. They are having a hanging like structures, and even though that boron has a 3 valency to accept the electron, it forms a 2 terminal hydrogen will be there, and thereby it forms a structure of banana, okay, which is also known as what? Banana bond. Next is uses of the boron and its compound. First, we will see the uses of boron. Boron is used to dope the silicon and germanium semiconductor that you are going to study in detail in your first PUC, that is in a solid state. Okay, the boron oxide, which is used in a glass making as well as in the ceramics, and borax, which also used making in the fiber glasses, in the cleaning fluid, as well as in a water softening, insecticide, as a herbicide, as well as a disinfectant also, as we are using a borax, and boric acid, which is used as a mild antiseptic and a flame reductant, and boron nitrate as a better thermal and a chemical stability. Hence, the boron nitrate ceramics are used at high temperature equipments, and boron carbide used in tank armor as well as the bulletproof vest. Next, with the aluminum uses, okay, it is used in transportations of automobile, aircraft, trucks, and in railway cars, marine vessels, etc. Even in a bicycle also, in packing of foils as a Aluminium foil we are using, usually as a cans also we are knowing, and all are also used in a water treatment, and in the construction for the windows, doors, and in the siding we are using the aluminium, and for cooking utensils, and in the electrical transmission lines of power distribution, and in a super purity of the aluminium, which is also used in electronic and CDS, and powdered aluminium will be used in a paint as well as with the pyrotechnics such as a solid rocket fuel and thermite, etc. Alloys, in making the alloys, especially with an aluminium with the magnesium and duralumin, will be mainly used by making the alloys with the aluminium. In the next session, we are going to discuss with the group 14, that is a carbon family elements. So what are all the things which I covered in this session? It is very important for the examination point of view. Have a look on it. We'll meet you with the next session. Till that, take care, be safe. Thank you.